Atoms and molecules can only exist at certain fixed energies, much like a person can only stand on discrete steps of a staircase. These discrete energies are called energy levels, E1, E2, and so on. A transition from a higher level E2 to a lower level E1 can happen in two ways. It can emit a photon, light, or the particle can absorb a photon and move upward. The likelihood that a particular transition occurs in a given small time interval is called transition probability. In quantum mechanics, the probability per unit time is expressed with a rate constant. For an electric dipole transition, the rate is proportional to the square of the dipole matrix element, the absolute square of the dipole matrix element between state 1 and state 2, and to a factor that depends on the frequency nu of the emitted or absorbed photon. Selection rules, for example delta L equals plus or minus 1 for atoms, act like traffic signs that tell you which stairs you are allowed to step on. The larger the matrix element, the easier it is for the atom to jump, just as a wider stair makes it easier to climb. Einstein introduced three coefficients to describe the three basic ways light interacts with a two-level system, levels 1 and 2. Spontaneous emission, a photon is emitted without any external field. Rate equals a sub 2 1 times n sub 2. Stimulated emission, an external photon of frequency nu prompts the excited atom to emit a second identical photon. Rate equals b sub 2 1 times rho of nu times n sub 2. Absorption, a ground state atom absorbs a photon and goes up. Rate equals b sub 1 2 times rho of nu times n sub 1. In thermal equilibrium, with a black-body radiation field of energy density rho of nu, the population of the two levels follows the Boltzmann law. N sub 2 over n sub 1 equals exp of negative h nu over k bt. Setting the total upward and downward rates equal gives b sub 1 2 times rho of nu times n sub 1 equals a sub 2 1 times n sub 2 plus b sub 2 1 times rho of nu times n sub 2. Dividing by n sub 1 and using the Boltzmann relation, Einstein solved for the coefficients and obtained two important connections. B sub 1 2 over B sub 2 1 equals 1, and a sub 2 1 equals 8 pi h nu cubed over c cubed times B sub 2 1. The factor 8 pi h nu cubed over c cubed is exactly the density of electromagnetic modes in free space, showing that spontaneous emission is really the atom coupling to the vacuum sea of modes. Explanation: the spontaneous emission rate of 2-1 tells how fast an excited atom will dump its energy when left alone. The inverse of this rate is the radiative lifetime tau. Tau equals 1 over a 2-1. For an electric dipole transition, quantum mechanics gives a more detailed formula. A 2-1 equals omega cubed times the magnitude of d2-1 squared, divided by 3 pi epsilon naught h bar c cubed. Where omega equals 2 pi nu is the angular frequency, d2-1 equals left angle bracket 2 vertical bar d vertical bar 1 right angle bracket is the dipole matrix element, epsilon naught the vacuum permittivity, and c the speed of light. Analogy: think of a spring-loaded toy that once released slowly unwinds. The stronger the spring, larger dipole moment, and the faster the unwinding speed, higher omega, the quicker the toy returns to its rest position. Just like a larger a 2-1 gives a shorter lifetime. In practice, the measured lifetime of the ND:YAG laser transition 1064 nanometers is about tau approximately 230 microseconds, giving a 2-1 approximately 4.3 times 10 to the 3 per second. When a photon of the right frequency meets an excited atom, it can trigger stimulated emission and the atom behaves like a tiny copy machine, producing an identical photon. The effectiveness of this process is measured by the stimulated emission cross-section sigma e, units of area. Sigma e of nu equals lambda squared divided by 8 pi n squared times b21 times g of nu, where lambda is the wavelength in the medium, and its refractive index, and g of nu the normalized line shape function integral of g of nu d nu equals 1. The gain coefficient g, often written as gamma, tells how fast the intensity of light grows as it travels a distance z in the medium. di over dz equals gi. G equals sigma e times n2 minus sigma times n1. where N2 and N1 are the excited state and ground state population densities, and sigma A is the absorption cross-section, equal to sigma E for a perfectly symmetric two-level system. Real-world picture. Imagine a crowded hallway where each person atom can either hold a megaphone excited or be silent ground. A passerby photon shouting a specific phrase makes all megaphone holders repeat the phrase louder. The louder the crowd, higher N2, and the more effective each megaphone, larger sigma E, the faster the overall sound level, optical intensity builds. Typical values. For ND:YAG at 1064 nanometers, sigma E approximately 3 times 10 to the minus 19 square centimeters. With an inversion density N2 equals 1 times 10 to the 18th per cubic centimeter, the gain coefficient is G approximately 0.3 per centimeter. Detailed balance means that at thermal equilibrium, every microscopic process is exactly compensated by its reverse. Applying this idea to the three Einstein processes leads directly to Planck's law of blackbody radiation. Starting from the equality of upward and downward rates, see the derivation of A and B, and inserting the Boltzmann population ratio, we obtain an expression for the spectral energy density of the radiation field. Rho of nu equals a 2 1 over b, 2 1 times 1 over open parenthesis exponential of open parenthesis, h nu divided by k sub bt close parenthesis minus 1 close parenthesis. Using the Einstein relation, a 2 1 equals 8 pi h nu cubed over c cubed times b21. The profactor simplifies, and we recover the familiar Planck formula. Rho of nu equals 8 pi h nu cubed over c cubed times 1 over open parenthesis exponential of open parenthesis, h nu divided by k sub bt close parenthesis minus 1 close parenthesis. Analogy: think of a busy marketplace where traders, atoms buy and sell identical objects, photons. Detailed balance is the condition that the number of objects entering the market equals the number leaving, resulting in a steady state price, the radiation intensity that depends only on the temperature of the market. This derivation shows that spontaneous emission is not an ad hoc addition. It is required to satisfy detailed balance and to obtain the correct blackbody spectrum. For a simple two-level system, the populations N1 ground and N2 excited evolve according to colon. dN2 over dt equals negative a 2 1 times N2 plus b 1 2 times rho of nu times N1 minus b 2 1 times rho of nu times N2 period. The first term is spontaneous decay, the second term is absorption, and the third term is stimulated emission. Because N1 plus N2 equals N total, the total number of atoms is constant. We can rewrite the equation in terms of the population inversion delta N equals N2 minus N1 colon. d delta N over dt equals negative open parenthesis a 2 1 plus b2 1 rho close parenthesis delta N plus open parenthesis b1 2 plus b2 1 close parenthesis rho N total period. In steady state, d delta N over dt equals 0, the inversion becomes colon. Delta N sub SS equals open fraction numerator open parenthesis b1 2 plus b2 1 close parenthesis rho N total close parenthesis divided by denominator open parenthesis. A 2 1 plus open parenthesis b1 2 plus b2 1 close parenthesis rho close parenthesis period. Because for a true two-level atom b1 2 equals b2 1, the numerator is never larger than the denominator, and the inversion never becomes positive, i.e. N2 is less than or equal to N1. This is why a population inversion, the essential condition for laser action, cannot be achieved with just two levels. Practical lasers therefore use three-level or four-level schemes, where the lower laser level is quickly emptied to an even lower state, effectively making N1 small. Condition for inversion colon delta N greater than 0 if, and only if N2 greater than N1. In multi-level lasers, this is obtained by pumping atoms to a high-energy reservoir and letting them relax non-radiatively to the upper laser level while the lower laser level is depopulated. Practical picture colon imagine a two-story building where people atoms can either stay on the ground floor, level 1, or go up to the first floor, level 2. If there is only a staircase connecting the two floors, you cannot have more people upstairs than downstairs because each person that goes up must come from downstairs. Adding a basement, third level, or a rooftop, fourth level, gives you extra routes to move people around, allowing more upstairs than downstairs. The spectral line width of an optical transition tells how sharply the emitted photon frequency is defined. Two main broadening mechanisms are important. Natural lifetime broadening. Because the excited state lives only for a finite time tau, the Heisenberg uncertainty principle gives a frequency spread. Delta nu natural equals 1 over 2 pi tau equals a 2 1 over 2 pi. This is an intrinsic property of spontaneous emission and appears in both spontaneous and stimulated processes. Doppler broadening. Atoms in a gas move with a thermal speed distribution. The observed frequency is shifted by the Doppler effect, leading to a Gaussian profile of width. Delta nu d equals nu 0 over c times the square root of open bracket 2 k sub bt ln 2 divided by m close bracket, where m is the atomic mass. Other contributions include pressure collision broadening and inhomogeneous broadening in solids. In spontaneous emission, the emitted photons inherit the full natural line width because each atom radiates independently. In stimulated emission inside a laser cavity, the cavity selects a narrow set of frequencies. The longitudinal modes and the gain medium can preferentially amplify a narrower part of the homogeneous line. This effect, called gain narrowing, makes the laser output much narrower than the original spontaneous emission line. Example: the neodymium YAG transition at 1064 nanometers has tau approximately 230 microseconds, giving delta nu natural approximately 0.7 kilohertz. In a room temperature gas, the Doppler width might be several gigahertz, so the observed fluorescence line is dominated by Doppler broadening. A neodymium YAG solid-state laser, however, can have an output line width of only a few hundred megahertz or less, because the crystal lattice eliminates Doppler motion and the cavity further narrows the line. The total line width is often approximated by a convolution of the homogeneous natural and inhomogeneous Doppler profiles, giving a Voigt profile. Section A Einstein A and B for ND:YAG, 1064 nanometers. Wavelength, lambda equals 1.064 times 10 to the minus 6 meters, leads to frequency nu equals c divided by lambda equals 2.82 times 10 to the 14 hertz. Measured radiative lifetime, tau equals 230 microseconds. Spontaneous emission rate. A 221 equals 1 divided by tau equals 4.35 times 10 to the 3 per second. Using Einstein relation, a 221 equals 8 pi h nu cubed divided by c cubed times b221. Solving gives b221 approximately 3.5 times 10 to the minus 20 cubic meters joule to the minus 1 seconds to the minus 2. Because b12 equals b221, this is also the absorption coefficient. Section B, stimulated emission cross-section. Take a Lorentzian line shape with full width at half maximum delta, nu equals 5 gigahertz. The peak cross-section is sigma E max equals lambda squared divided by 8 pi n squared tau delta nu. Assuming refractive index n approximately 1.82 for YAG. Sigma E max approximately 3 times 10 to the minus 19 square centimeters. Section C, gain coefficient. If the pump creates an inversion density, N2 equals 1.0 times 10 to the 18 per cubic centimeter, and the ground state density is N1 equals 5.0 times 10 to the 18 per cubic centimeter, the net gain is G equals sigma E times N2 minus sigma A times N1, which simplifies to sigma E times N2 minus N1, approximately 3 times 10 to the minus 19 times negative 4 times 10 to the 18 equals negative 1.2 per centimeter. The negative sign shows that with these numbers we have no inversion. To achieve positive gain, we need N2 greater than N1. For example, pumping to N2 equals 6 times 10 to the 18 per cubic centimeter yields G approximately 0.6 per centimeter. Section D, laser threshold. For a standing wave cavity of length L equals 1 meter with total round-trip loss alpha total equals 0.1 per meter, the threshold gain is GTH equals alpha total approximately 0.1 per meter equals 0.01 per centimeter. Thus an inversion that provides G greater than or equal to 0.01 per centimeter is sufficient. Using the cross-section from section B, the required inversion density is N2TH equals GTH divided by sigma E, approximately 0.01 divided by 3 times 10 to the minus 19. which is approximately 3.3 times 10 to the 16 per cubic centimeter. This is a modest density, easily reached with typical flash lamp or diode pumping schemes. These sample calculations illustrate how the abstract Einstein coefficients, cross-sections and lifetimes become practical numbers that engineers use to design and optimize lasers.